Hello, my name is Irfan. I'm a student of BDA 2511, and today we will solve exercises of discrete mathematics. We are starting from A, and to solve this, we start with the definition of logical equivalence. Since A and B are equivalent, they must have the exact same true values in every scenarios. So, since A plus B, then saying that equals to B. Now let's look at the OR operation. We need to prove that adding statement C to both sides doesn't change the fact that they are equal. So the easiest way to show this is to test the two possible cases for C. For situation C, the first one is if TC equals T, then TA with C equals T, and the TB with C also equals T. So since both sides result is true, they are equivalent in this case. So that's the first case, and now the second case. And in the second case, we try a scenario when TC equals false. So then T conjunction C equals to A, and the TB with C equals to TB. So if C is false, the result of the OR operation depends on the first statement. Because we know from the start that A and the B have the same value, the result will match here as well. So that means that T A C equals to T B with C. In all cases, that means that A C equals to B with C. So since the true values match whenever in every scenario is true or false, two exceptions are logical equivalent. Part A is done. So now we are going to part B. In part B, we need to show exactly the equivalent. Let's see. So again, we will break it down by looking at what happens when the situation C changes. So the first case, if C is false, then T A C is false, and the T B with C equals also false. So when C is false, and the operation automatically becomes false for both sides. Since false equals false, the equivalent false, and they are equal. So the second case, it's if situation C is true, then TA C equals true, and B with C also the same, and the C is true result is determined by the first statement. Since A is B is equivalent by definition, both sides will be the same true value. So that means that A C equals to B with C. Now we are going to chapter 2 and section 1, exercise 7. Section 1, exercise 7. So here we need to determine if it's true or if it's false. So the first A, it's true. The empty set is a subset of every set, including itself. This is fundamental rule in set theory, so that's quite easy. The B, again, again, the empty set is a subset of any set. Even if the set on the right contains an empty set, the rule still applies, and that's also true. So going to see where this situation. So the empty set has no elements at all, therefore nothing can be inside it or belong to it, so it's not even itself, and that's gonna be false. Now we are going to D. We have that kind of situation, and in this case the set on the right contains one element, the empty set. Since we can see it sitting inside the brackets, the statement is true. So now we are moving to E. Now we're moving to situation E. Here in situation E, the claim 1 and 2 is not a subset, however both 1 and 2 are present in the set on the right, so it is a subset, making this statement false. So here is gonna be false. Situation F, we are looking for the package 1 and 2 as a single element. We see 1, 2 and 3 and a large packet, but not the specific pair 1 of 2 and 2, so it's false. So if we're moving to G, the symbol means proper subsets of 1 and 2, so it's a subset, and since the right set has an extra element, it is proper 1, and it's true. H, look closely at the brackets. The right set contains 1 and 2, and the 1 and 2, here is 1 and 2, and here is also 1 and 2. The single bracket version of here and here, and the single version of 1 and 2 here, it's not there, so it's gonna be false. To check if it's a subset, we'll look at its element 1 and 2. Is element on the right side? Yes, it's a right there at the end, so it's true. Now we are moving to section 2 and beginning with the second exercise and beginning with the punct A. So here we need to find that this kind of situations, and let's start by defining the intersection and union of Z and T. We know that this is power of 2, square root of 2, and the intersection S of T includes only the elements that appear in both sets, so there's 25 and the square root of 2. The union of this combines all unique elements from both sets, and I will list everything from S first, then add the new items from T. So here is 2, 5, square root of 2, 25, P to power of 3, 2 divided by 3, and 6, and also half of 3. So the Cartesian product creates pairs where the first element is from T and the second is from our interaction result. There's a 5 elements in T and the 2 in the intersection, so we will get 10 pairs here. The pairs is this pair. I'm sorry for this. So we will have 10 pairs here. The pairs is looking like that. It's 4 and the square root of 2, then 4 and 25, then it's 25 and the square root of 2, and then it's 25 and 25. The next pair is square root of 2 and the square root of 2, and the next pair is square root of 2, 25, and the next is 6 square root of 2, then it's 6, 25, and then 1 over 2 square root of 2, and 1 over 2 and 25. Now we compare our sets to the set of all integers that are denoted by z. So here we can the union z with s. It's going with square root of 2, p, and 2 over 3. So the union z and s includes all integers plus the irrational and the fractional numbers from s. It's square root of 2 and p. The intersection z and s pulls only the whole number from s, that is 2, 5, and 25. So this 2, 5, 25. Then similarly for t, the union is all integers plus square root of 2 and 1 over 2. So here is z2, to z square root of 2 and 1 over 2. So here in the intersection gives us the integer 4, 25, and 6. 4, 25, and 6. And that's all. Now we're moving to exercise 3. In exercise 3, we have that we're given that 8 is including that kind of pairs. 5, 0, 0, 6, minus 5, 5, 1, and the 3, 4, 3. Spoken script for in the task, we take each coordinate pair A and B from set A and find the sum of A and B. So here we're beginning with this one. It's gonna be minus 1 plus 2 is gonna be 1. 4 plus 5 is gonna be 9. 0 by 0 is 0. 6 plus minus 5 is 1. 5 plus 1 is 6. And 4 plus 3 is 7. So in the result we have that kind of result: 1, 9, 0, 6, and 7. So here we look for the first coordinate A, but only if it's a positive number. The pair minus 1 and 2 and 0 and 0 do not count because minus 1 and 0 are not greater than 0. Our set contains 4, 6, and 5. So it's from 5 it's 4, from 6 and minus 5 it's 6, and from 5 and 1 it's 5. So and from 4 and 3 it's 4. So the result, how I said, we have 5 or 4, 6, and 5. It's our set. So now we are going to see, that's B, and now we're going to see. Here we're looking for the first coordinate A, but only if it's positive. Oh no, that's a B, sorry. Here we finally look for the second coordinate of B, but only if it's a perfect square, like 0, 4, 9, and 1. So it's gonna be like square. So, and for color, and taking from -1 and 2 gives 2, and we're checking all b values. Only 0 and 1 are perfectly square, so the result set is have to be with 0 or 1. We have here 2, so it's not for us. From 4 and 5, it's 5 also no. From 0 and 0, it's perfectly 0, so that's gonna be yes. That's perfectly suited. And here the 0 and square value is still 0. So from 6 and -5, we're taking -5. No, that's not our meaningful result. From 5 and 1, taking 1. And 1 square is also 1. And from 4 and 3, there is no any values that are right for our set. So in the result, we have here 0 and 1 sets. Part C, we are looking at combined operation. First, let's find the intersection of S with the union of S and T. So we know that notice that the union of S and T contains everything in S. So when we intersect that back with S, we just get S itself. This is a great example of absorption law. 2, 5, square root of 2, 25. So if we are doing this, the result is 2, 5, square root of 2, 25, t. So the result is just 6. Now for the second part, we'll take the integer from S and the integer from T and unite them. This gives us the set of 5 whole numbers. Taking from this set and this set, so we will get, after the result, we'll get that kind of pairs, that kind of sets. It's 2, 5, 25, 4, and 6. The main thing to notice here is that this is what we simplifies perfectly back to S, and it's a logical shortcut. Now we are going to do. Finally, let's look at this part, which deal with the distributive-like properties. So here is know that it's going to be reset square root of 2, 25. So why we have that kind of results? For the first list, we take all integers z and add the elements that S and T share. Since 25 is already an integer, we only need to add square root of 2 to the set. So, and now if we find the union of z with S and the z with T separately and then intersect them, we will see that only on integers. Here you need to take a look. So here you can see that the only non-integer they are both have is square root of 2. The result is the same as the first calculation, so it's going to be just square of 2. So So you will notice there is the two results are identical. This determines the law of union over intersection. For this, is need to be one-to-one. Each of the three elements in X needs a unique partner in Y. That's for choices for the first, 3 for the second, and the second for and the 2 for the third. Total is 24. So here's 24. Totaling is 24. But for either to X we have more items that partners, so it's impossible. The answer is 0. Here the answer is 0. Now we are moving to B. Here we have kind of, here will be 0. For function to be onto, every element in the distraction must be hit. For X to Y, we only have 3 inputs, but for output so cover, so we can't hit them all, so that's why here is 0. But for Y to X, we use the formula for onto functions, which give us 3 and the power of 4, which is 36 possible mappings. To find g of f, we plug the entire formula for f into g. Since g just flips the fraction, we get this one. We have these results. Here we have g of x plus 1 divided by x plus 1. So that after we solve in the result, we will get x plus 1 over x. So to find, now we doing this reverse. For reverse we need to do this to find f of g. We need to put 1 over x into f. So, and it's gonna look like f of g x f divided by x divided by x and divided by x plus 1. So if we simplify, that's gonna look like it's x1 plus x divided by x. So in the results we will have just 1 divided by 1 plus x. Here is the results. Now there is a triple composition. We already know g of f, and now we just apply h, which means adding 1. Here we need to find h g of f of x. So it's gonna be looking like h of g plus 1 plus 1. So that's gonna be like x plus 1 plus x divided by x. The result will have 2x plus 1 divided by x. So that's the result. But if we now find f of g from x, from hx, finally we'll go the right to left, h, then g, and then f. After plugging everything and simplifying, we will get these results. It's gh x 1 over x plus 1, and if we are adding here, it's gonna look like f1 over x plus 1, and that's gonna look like 1 over x plus 1, 1x plus 1 plus 1. So in the result we will have